Okay, what we're doing now, I'm going to show you the answers to the last example in section 4.4 notes, that example 6. But what I wanted to do was to kind of use what you should have done as a springboard to the curve sketching section, which really is not new information. It's basically you just putting together everything that we've learned in chapter 4 to help us come up with the graphs of these functions. Now, just as a kind of reminder, and this is in your note packet for section 4.6, but we pretty much have basically had this idea that everything that we're doing is in order to come up with an accurate graph of a function without a calculator. And that there are some guidelines that we've been following. The analogy that I've started using in my Algebra 2 class is that right now we're going to set you loose into a very, very dark room, a room that has no windows, no doors, and no light. And we're going to let you stumble around in the room until you figure out what the function looks like. And what we're going to do is we're going to give you some tools to help you find lights and switch them on so you can illuminate parts of the graph. And so when we were in pre-calculus, we spent a lot of time working on how do we find the domain of a function, how do we determine and name any discontinuities of the function, your holes and your vertical asymptotes or your jumps. We also looked for analyzing our end behavior, which actually came back again this year. That was your section 4.5, which, if you will recall, we taught that section back when we were doing limits in chapter 2, and so that was the limits at infinity section. So you might want to review that prior to working on the 4.6 material, just to make sure you still understand that. You can go back and view the 4.5 video. That will give us our end behavior, our horizontal asymptotes, our slant asymptotes, and our other asymptotes. Finding your intercepts is pretty straightforward. Finding any symmetry. Using symmetry to determine if you have symmetry over the y-axis or symmetry over the origin. And then once we've done that, then this year we've been expanding your tool set. We've been allowing you to turn on more lights about the function. Determining what intervals the function is increasing and decreasing on using your first derivative for your increasing-decreasing test. Finding your relative extrema, either using the first derivative test or the second derivative test for relative extrema. Then we also gave you some tools about determining where the function is concave up and concave down and points of inflection. So you're using the second derivative for concavity test. And then basically you're going to be able to connect the dots. And so the idea was, for example, we're going to look at the very first part A in example 6 from the section 4.4 notes. Some things that you should have done as you were working along with it. You want to make a note that your domain is negative infinity to infinity. That the function was a continuous function, although it does have a cusp alert because of the cube root. So that's going to tell us it may not be differentiable, but it's definitely continuous. Went ahead and did the pre-calculus stuff first, found where the x-intercepts were by letting y equal 0, factored my polynomial, or well, not really polynomial, factored the combination of power functions, and set them equal to 0, and so that I could determine the x-intercepts. I then did a quick test for symmetry to see that it did not have special symmetry, that I do not end up back with the original function. So that's something to keep in mind as I am sketching the graph. Came through and did my end behavior, where it's kind of the start of calculus, where did the ends go? Using the fact that in power functions, when you add them together, it follows the largest power function and with a positive lead coefficient, and then I examined what was happening as x went to infinity. This would go to infinity, and as x goes to negative infinity, it went to negative infinity. We can go down, and now I found the first derivative to use, because I'm going to do the first derivative test and the increasing-decreasing test. I went ahead while I was here and found the second derivative so that I could do the second derivative and test for concavity, and then use the second derivative to help me for points of inflection, or extrema, however we want to look at that. And then once I had this, I also looked at this and realized that the domain of f prime is also all real numbers. So that told me that the original function was differentiable everywhere. So I have a continuous and differentiable function that has no cusp and no vertical tangents, right? And no discontinuities. I then use my first and second derivative to create a sign chart to organize the information. Now you can either, as I have done here, I put them both on the same sign chart because I'm really trying to separate out what's going on in each of these sections. Now what you might like to do is to separate them into two because it might get a little confusing when you're looking at this. Like I technically should probably add, since 0 is a relative max, and then I was decreasing over in this section, that this decreasing is for this entire section. So what I know about the function after I finished this was that it was increasing in concave down until I got to 0, and then it was decreasing in concave down until I got to 1. But then that didn't really change, and it was still decreasing in concave down all the way, it's decreasing but concave up once I hit past 1, because that's where that's why a little bit of putting this on the same graph can get a little confusing. You have to be kind of really clear about what you're doing. It may have been better for me as I was doing this to spread these out a little bit and make sure I really show what f is doing. In fact, I'll do that and we'll come back and we'll pause it for a sec. Alright, coming back and looking at it, just cleaned it up just a little bit. And this is also partly the reason why they don't interpret your sign charts on the AP. That laying it out a little bit nicer for you, being more neat in my work, you can see that the first derivative is positive, the second derivative is negative, so I'm increasing in concave down. 0 was a critical value for the first derivative, and I did switch, so I have a relative max there. And it switched from increasing, the function switched from increasing to decreasing because the first derivative switched from positive to negative. At that time, the second derivative was still negative, so that ended up giving me a concave down section. Then we ended up being negative for the first and positive for the second, so I'm decreasing in concave up. And because the second derivative switched sign, I had a point of inflection. And then we had a critical value at 8. And coming here, we had a negative and then positive on the first derivative, so it's a relative min there. And then I've switched to increasing and concave up at that point. So we have all of this information, and then you have to go sketch it. And the idea is to take the important points that we've identified, your x-intercepts. Then I took my relative min. That was a relative max already in the list. So my relative min, and I went and got the y value for that. And then you get your points of inflection. So 1 was a point of inflection, and I added that in. Now that gave me on this graph essentially these, not that point, but this point, this point, this point, and then your x-intercept over here. And then I felt like I needed another point because it was kind of bare over on that side, so I went ahead and plugged in and got an additional point. And then from there, following the rules that I am increasing in concave down until I got to 0. There was a relative max, and then it was decreasing in concave down. Then I hit 1. And at 1, I had a point of inflection, and it was still decreasing, but now concave up to my relative min of 8, and then increasing for the rest of the way and concave up. And so the idea is, and then once I go and say, well, what did it look like on my calculator? Like you can see, we're pretty darn close to what that is. That, you know, if our scale and we were on graph paper, we'd probably be right on the money of what it is. Now, I did take a look at this one. Just make this smaller now so we can see that. The other interesting about this is I did look at that because you're like, oh, that looks like a cusp. It's pretty sharp right there. But remember that in order to be a cusp, the first derivative would be undefined, and we did not see that. So even though this is a very sharp turn, this is not a corner. This is not going to be the actual cusp. And it was possible, remember that we said that if there is a tangent line there, you should be able to zoom in until the graph appears as a straight line. Now, I practiced this with my calculator and I did zoom in really, really far. You had to zoom in a lot in order to get it, but it did eventually start to level out and become a horizontal line.